share the screen with you, talk about what we're going to do today. I did want to say that I sent something to you, or I put it on Moodle, I think, a link for like that thing that was the multiple choice and true false. That's kind of a really good review of that long section we did in 4.1 because it lays all the groundwork, and some of them are kind of sneaky. And I will put the I'll put the key up for you to make sure you've got it right. And if there are questions about it, I'll answer those on Wednesday. But that's a really good exercise. It's hard to find multiple choice and true false exercises to do. Let me go ahead and share the screen, and then we'll talk about reduction of order. Come on, let's go. There we go. We made it through 4.1. The rest of the chapter basically is now we're going to figure out how do we actually find these solutions that form a fundamental set, or that are a particular solution. So that's actually, and that's kind of the heart of this course, is chapter 4, much like finding out how to take integrals was the heart of Calc 2. So let's talk about this. We're going to start slowly at first, and we're going to talk about what if we know one solution of a fundamental set. And we're going to do it in a really easy case, and that's where we have a second order DE here. So this is sort of my generic second order DE with the coefficients A2, A1, and A0 continuous. And as usual, this one not zero, and that's going to come up in my discussion. So that means if we know one part of the fundamental solution or the fundamental set, if it's a second order, we only have one more to find. So that's why we're going to make this a little easier. So there would be two linearly independent solutions there. So what we're doing is looking for the other one. All right, so we're going to look for the other solution. So we're given one, we're going to look for the other. Okay, let me give you an example, and then I'm going to work one. I'm going to work one specifically, a specific equation, and then I'm going to go through it generically. Something turns out really nice when we actually do the proof of this thing. So so if you look at this one right here, all right? You look at that one right there, y double prime minus y equals 0. Can anybody, I mean, looking at what happens there, you double differentiate something, then you take away the original and you get 0. Once again, I'm asking you to say, well, by inspection, we know that's got the trivial solution, but we know the trivial solution cannot be a part of a fundamental set. Because if you put that in the Wronskian, if you put 0 as a function in the Wronskian, you're going to get a column of zeros. And that indicates that the determinant would be 0, so it wouldn't be linearly independent. So we're not going to consider that one. Does anybody see one that they think might work? And again, think sort of a really basic function that's easy to differentiate, and maybe you can figure out when you plug it in and double differentiate and subtract the original, it'll be 0. And take your mic off if you got an answer. Anybody figure out which one might work there? Differentiate it twice, take it away, and you get 0. Yeah, e to the x, exactly. All right, so what my guess here, and it's not such a big guess, it's right, because if you differentiate that twice, you'll get e to the x, and then when you take away the original e to the x, you'll get 0. So we know one of the fundamental set, and we want to find the other one. All right, now, guys, I want to go back. I want to do this problem right here specifically. So I'm going to go away from my general notes, but my goal before I move away from the screen is that given a second order linear homogeneous DE, we're working with homogeneous now, we're not working with non-homogeneous, and a known solution. So in this case, our known solution is e to the x. Find a second linearly independent solution to form a fundamental set. If we find that second independent solution, we can write the general solution to the homogeneous one. So let me go back And what I want to look at is this one, the one that we just looked at. And I want to talk about a method that's going to come up a couple more times in the course. So I think it's a good idea to look at a specific one, and then I'll look at generically how this thing is working. Okay, so the title of this method is called reduction of order, and it's literally going to do that. What we're going to do by a simple substitution here is look at that DE and say to ourselves, well, it's second order. I really don't know how to solve that. Or at least all I could do was guess that one of the solutions was e to the x. Reduction of order takes something of a higher order and reduces it to a lower order. So what we're going to do with this second order DE is reduce it in order by 1. And if we reduce it in order by 1, it would be a first order linear DE. Or I'm going to show that. And we know how to solve first order linear DEs. We can separate them. We can find integrating factors. There's all kinds of stuff we can do. So here's how I want to start this thing. We've got this. That's what we're trying to find the other solution to. We know one of them is e to the x. All right. So why we want to find a second solution. C e to the x, if you say, well, why don't you just multiply the solution you've got by c e to the x? Well, then I wouldn't have a linearly independent set. Let me show you something. If I said, what if we started with e to the x and c e to the x, c1 e to the x, and we looked at the Wronskian. So that thing right there is the Wronskian. And we differentiate in this column and we get e to the x and e to the x. And in this column, we differentiate and we get c1 e to the x again. If I find the Wronskian by doing the determinant, remember it's crossing here and crossing there and subtracting, you'll get this thing minus that same thing and you'll get 0. So when we're looking for a linearly independent solution, it cannot be a constant multiple. So that's going to drive sort of my search here. So I'm going to go back and say, since y c e to the x or c1, whatever, would not be linearly independent, we assume that a second solution is of the form u of x times e to the x. In other words, it's not a constant multiple. It's something times a function that's not a constant. Now, this is just a guess. And you say, well, why am I even multiplying it by e to the x? How do I know it has anything to do with e to the x? Well, I don't really, okay? But I'm going to put that, and that thing is the one we know. So we start by this guess for our linearly independent solution we're looking for as being some function of x, which I'm going to call u, times the one you know, okay? Times the one you know. All right. All of this is in the book. It's a little messy. If you want to write it down, that's fine. I'm going to go through it step by step to show you what I'm doing. But it is in the book if you just want to watch and kind of leave a space there to write it down. So if I'm supposing that this thing right here is a solution to that DE right there, all right? In other words, that DE actually equal to 0. Then the thing I'm going to do is find y, well, I know y, I know my guess for y prime and y double prime. And what I'm going to do is plug all those things into here, the original equation, and see what it takes to solve that. See what has to happen here. So taking the derivatives, guys, this is u e to the x. I'm going to have to use the product rule. So it'll be first times the derivative of the second, which is just e to the x, plus second times the derivative of the first, which I'm just going to mark as u prime. There's the first derivative. I really don't need that one to plug in here, but I do need y double prime, so I need to get to it on the way there. So I'm going to take another derivative, and this is the one I'm taking the derivative of now in order to find y prime. This one's going to use a quotient rule again. I mean, not a quotient rule, a product rule. First times the derivative of the second, e to the x, plus second times the derivative of the first, which is u prime. The next piece, this e to the x u prime, I'm going to use a product rule again. It's going to be first times the derivative of the second. Actually, that went right here. First times the derivative of the second plus second times the derivative of the first. So that's what that looked like right there. So first times the derivative of the second plus second times the derivative of the first. Guys, that got cut off. This should be an e to the x there. Sorry, my scanning abilities or whatever. So again, that last one is first times u double prime plus u prime times e to the x. That doesn't look good, but what I did, and I'll show you, that's not the form I'm going to use. If you look at this now, what you've got is a u e to the x. You got two of these things, and that's the one that got kind of messed up at the end. So 2 e to the x u prime. So that's this one plus this one with the correction. And then plus, and that's two of those. And then the last one is e to the x u double prime. Okay. So I found all the derivatives. I'm now going to plug them into here. Okay. So my u double prime is all of this. All right. And then minus my y, the thing that I'm guessing or trying to find as a solution is some u e to the x. So I plug it into the dE. One thing drops out, the first and the last term right here. And I'm left with this, and I'm going to write it in this form. I'm going to write u double prime e to the x plus 2 e to the x u prime. That's just what's left after what drops out after you plug it into the dE. Okay, so I'm right here. That's a second order dE. So you say, well, what did I gain by that? Well, nothing yet. But I do see that there's an e to the x in every term, so I'm going to divide everything in there by e to the x. Okay, so I've got u double prime plus 2u prime equals 0. All right, let me stop for a breath. What I'm going to see, what I see there, guys, is something that's second order, and it's got easy coefficients. It's got 1 and 2. And here's where the term reduction of order comes in. Reduction of order, I'm going to make a substitution to reduce the order of this thing. In other words, I'm going to let W here, just for briefly, I'm going to let W replace U prime. So, and they're both functions of X. So here's the substitution I'm going to make. And if W is equal to U prime, then U double prime is W prime. So W is U prime, W prime is U double prime. Okay, we'll scroll up a little bit. So I'm right here, having plugged everything in. And now I'm going to make my substitution. Okay, so in the place of U double prime over here, I'm going to put W prime. And in the place of U prime, I'm going to put W. Those were my substitutions. Now, what you see is that I reduced the order, guys. I reduced the order. I reduced this equation right here from a second order to a first order. From a second order to a first order. So I'm not doing anything hard at it, but it's a little bit of a process to get there. Now, that's linear. That's linear with P equal to 2. All right. So what I know is that I can find an integrating factor, which will be e to the integral 2 dx, all right, p dx, remember? And that what's going to be on the left-hand side is just going to be the derivative of the w that's in the linear thing and the e to the 2x. That's the integrating factor right there. And on the right-hand side is 0, because remember that original dE, y double prime minus y was equal to 0. So I'm going to integrate both sides, all right? And what we'll get going here is w e to the 2x, because I integrated the derivative of that thing. And again, this is just your technique for finding linears. I could have separated this two. It might have been easier. And I'm going to separate something a little later on because I think it probably is easier. But it's linear. Your book did it like that, so I did it like this. So that's w e to the 2x equals c. So if I divide both sides by e to the 2x, all right, I'll get w equals c e to the minus 2x. Now there's a c there actually. The integral of 0 was c. That's where I got that c. So I actually have my w. And it turns out that the c really doesn't matter on this thing, and we'll talk about that in just a second. But it doesn't make any difference, because if we know c e to the minus 2x is part of a linearly independent set, then this one is. Doesn't matter about the c. All right, so looking at that, I'll go back. I found w, and what w was e to the minus 2x. So if I integrate, now remember what I'm trying to do is find this this linearly independent solution. So if I integrate, I'll get minus 1/2 e to the minus 2x. So I'm just saying that c right there really doesn't matter. So I'm gonna just get rid of it. And then when I integrate both sides there, I'll get this thing, minus 1/2 c to the minus 2x plus c2. Now, I want you to remember what, yeah, Haley, yeah.
Where does the constant go in the step where you plug in u prime?
Let's see, where did I plug in u prime? Right, right here? Or,
Yeah.
Okay, right in here. I said you can put a constant there, but I really don't need the constant because I'm trying to find a member of the fundamental set. And remember, if one member of the fundamental set is something, then multiplying it by a constant isn't changing that fundamentally. They would not be two different things. Okay? So let's kind of remember what we were trying to do. So there's my u right there. And remember that, and this is where it gets starting to look a little nicer. My u, remember, was my guess of times the original function, all right, about what my new linearly independent solution should be. So I'm going to take this u, all right, and multiply it by y1. Well, here's this one. I'm taking that and multiplying it by y1. Now remember, y1's the one that I knew. So y1 is e to the x, right? So that thing right there is what we started with. We said, well, we know 1, we're going to call it y1. And I multiplied this y. The y that I'm trying to find is ux times the one I know. I've found u. So when I take this thing right here and multiply it by y1, I get, and I had trouble because I was sort of running out of room here. But when I multiply it out, I get this. Now notice what it looks like. Minus 1/2 c1 e to the minus 2x times e to the x, and let me erase that. That doesn't look very good at all. It's plus this thing right here. See that plus sign right there? It's that plus sign right there. This term goes on the end of that thing right there. But anyway, it's what you get when you multiply this by e to the x. Now, nice thing is we're not interested in the e to the x part of this because that's already part of a fundamental solution. So my choice is to let C2 be 0. So I don't really care about that. And if I want to find the easiest form of the independent solution, I'll let C1 be minus 2. Because minus 2 times minus 1/2 is just 1. That leaves me with just, what I'm doing is picking the appropriate constant to just lay bare the other fundamental, the solution in the fundamental set. And that's it. Y2 is e to the minus x. Y2. So, question.
We have u equals negative 1/2 c2. Where does that c2 come back in?
That's a C1 right there, okay? And then the C2 is up here.
Okay, where's...
Oh, I'm sorry. Yeah, actually, this thing right here should have been a C1. Sorry. That's
So,
mhm.
so would it be just more beneficial to us to just leave the C1 in there from the first place?
We could, but it's not. But we're just looking for the barest. We're not looking for the combination in the end yet. What we're looking for is just the barest part of what the function is. Not what it gets multiplied by, but what the function is. So your book, you'll see in your book, they'll say something like, well, let C2, and you know, I got, I'm sorry about this. This should have been that should have been a C1 right there, okay? So when I integrated this thing, it added a C2 on, and U was equal to that thing. Now, I don't really care. I'm trying to isolate the fundamental part here. And this has already gotten included in the fundamental set, the e to the x. That's why I let C2 be 0. The other one had this minus 1/2 C1 on it. So if I let that be -2, I'll just get 1 there. All I'm doing is just creating 1 times e to the minus x. I'm taking the barest, nicest part of that. I mean, I could put 5e to the minus x, and I'd have a linearly independent solution thing to go along with e to the x. And I'm going to show you that in just a second. But I don't care. I'm choosing the constant to be what I want to make it the easiest thing. Okay. And I'm sorry, my coefficients got a little bit, I mean, my subscripts got a little bit mixed up there. Okay. So let me go a little further. I think you'll see what I'm doing. What it says here then is that this thing that we just found is the barest form of what's another solution to that DE. And if you check it out, y double prime minus y, if you differentiate it twice and you plug in e to the minus x, you'll get 0. So that thing is a solution to that DE. Now, the only thing we really have to check to see if it forms a fundamental set at this point is whether the two are linearly independent. So we could use that, plug it in, we'll get 0. Now we've got e to the x, we've got e to the minus x. I just put it, I'm gonna go down here and say, well, okay, if that's what you say, it looks like you created this other linearly independent solution or piece of the fundamental set. We need to check it. The derivative of e to the x is e to the x. The derivative of this is e to the minus x times minus x. Just trying to see if those two things are linearly independent. Notice here, you'll get e to the 2x minus e to the 2x. Not true. Hang on. What do you get there, guys? What's e to the x times e to the minus x? What's e to the x times e to the minus e to the minus x? What are these? What's going to happen with those two exponents right there and there? You're going to get e to the 0 thing, and then minus going this way is minus that, going that way is minus e to the 0 there. Notice I get minus 1, which is minus 2, which is not 0, says it's linearly independent. Linearly independent. So with that reduction of order, I could solve it, and I found the second part of the fundamental set. Now, what that means in terms of what we did the other day, or 4.1, is that for this equation right here, y double prime minus y equals 0, the fundamental set is e to the x, e to the minus x, and the general solution, is y equals c1 e to the x plus c2 e to the minus x. Now, in answer to Haley's question from earlier about what about the C1 or what about the C2, I mean, you get it back here because that says, okay, and a solution could be any linear combination of those two. So you're getting it back right here. Okay.
Could you
Haley?
scroll up again?
Who's that? I'm sorry, scroll up. Okay,
Yeah.
sure. Who is that? I can't see again. Okay. Let's see here. How far you want me to go?
Just up to where we keep going just a little bit.
Okay.
Where we concluded, yeah. So we y2 equals e to the negative x.
Yeah, and that was what, see what we, this was this whole string of things when I multiplied u times the known solution. U times the known solution was this term right here, which had an e to the x in it, all right, and an e to the minus 2x. And this, the 1 times c was just that thing right there, all right, because I was just multiplying by e to the x. Now, that's already, that thing right there is already part of my fundamental set. I don't need to consider it. This part, if I add e to the minus 2x and e to the x, I get e to the minus x. And that's why your book says, well, let's let the coefficient on the e to the x, which is already the piece of the fundamental set we know, let that be 0, okay? And let C2 be minus 2 to completely isolate just the barest form of the other linearly independent solution. Okay, it's getting kind of messy up there. But that's what it looks like. Let me do something here because it got so messy up there. Let me try something here. I'm gonna get rid of this and I'm gonna write down that step again. This was my u right here. And ultimately what I was trying to find was u y1, u of x times y1. So what I was finding in that step that got so messed up there was minus a half, all right, times C1 e to the minus 2x plus C2 times the one that I knew, the y1, which is the e to the x. And that's what I got when I multiplied it out. So what that's saying is that this piece of it doesn't really make much difference because we've already got that as a member. This piece of it is what makes the difference when you have the e to the minus 2x times the e to the x, and that part will give you the e to the minus x. And then we just let c be whatever it takes to get a coefficient of 1 on that. That's a little, it looks like a little bit of trickery, but that's what's going on there. Okay, questions, anybody? I'm going through this process again generically, so this might help. Now, on your homework, I've got one, and this is homework to hand in, and what I'm going to show you is how to do this generically. And what happens a lot of times in differential equations is that we can find a generic formula for things. In other words, in the process of proving it, we figure out how to do something. For instance, when we were doing linear equations, we figured out what the integrating factor used to be. So I'm going to look at this from a generic point of view. So I'm going back to that first screen that I looked at.
Dr. Harrell, we
Yes.
did to say there's a general solution of y equals C1 EX plus C2 to the negative x.
Yes, and the reason for that is I started with this known solution, and through that whole process that I just did, I found another linearly independent solution. Okay, and how do I write a general solution? It's just C1 times y1 plus C2 times y2. In this case, e to the x and e to the minus x. You want me to go back to what I did, where I did that? Anybody? That was just.
I was asking.
What?
I'm okay.
Okay.
I was sure I had it right.
Okay. All right. Anybody else got a question?
When you further down, if you scroll down a little bit, there was a part where.
All right, I'm gonna go. Hang on, Tierra. Let me get back to where I was here. Okay. Right in this one right here that I was just doing.
Yes.
Okay. What you want to see?
Right there where it says if e, and then it has the integral of 2.
That's not if. That's actually what that stands for is integrating factor, guys.
Oh.
My integrating factor. Remember, it was e to the integral p. So I was using the technique I learned up for the last test there to get an integrating factor.
Okay, that makes sense.
Okay, sorry about that. And as I said, this one would be really easy to separate. In fact, I'm going to do the separation in a minute. I mean, I could have put dw dx here, separated it, and I could have gotten the answer probably a lot quicker. I just kind of wanted to throw that in for the very reason that I want to remind you of integrating factors, okay? But I could have done it that way. It certainly would have looked nicer. Anybody else question about this before I go back to that other screen? Okay. So I'm gonna go back and look at this generically. So the question is the same. We're gonna try to construct another solution from a known solution. We've got this generic second order DE. A2 of X cannot be 0. And I'll show you why this method won't work unless that, or for any place where it can't be 0, because I'm going to ultimately end up dividing by it, guys, is what's going on. All right, so I want you to watch me here. I really don't want you to write this down until I get to the very end and I get to the punchline and you see what we've got, because I'm going to follow the same process, except I'm going to integrate a little differently as I did on that specific case up there. But I'm trying to do it generically because I think in the end, I can suck a formula out of this thing. Instead of having to carry this process through for every single one of these things I do, I think I can suck a formula out. And so let's try that, and then I'll give you kind of your book's take on which one to use. Okay, so here's my goal again. I'm given a second order linear homogeneous DE and a known solution, y1. In my last problem, that y1 was e to the x. Find a second linearly independent solution to form a fundamental set. In the last problem, the one I found was e to the minus x. I only need 2 because it's second order. That's all the theory coming out of that first section. Okay, if I've got second order, I got 2 linearly independent solutions. If I've got third order, I should have 3. No more, no less. Okay. All right, so here's my method. First thing I'm going to do is divide by, let me look back at this thing. I'm going to divide by A2 of X. So if you look at the original, I'm going to divide by, up here, I'm going to divide by that A2 of X. And when I divide by that, I'm going to call what I get, this would be A1 of X divided by A2, and this would be A0 of X divided by 2. I'm just going to call them P and Q. I'm not going to drag all those A2s and A1s and so forth all the way through. But I just divided the whole equation by A2. And when you do this process, that's the first thing you have to do if you're doing it what I call the long way. So it says we're going to divide on an open interval I where P of X and Q of X are continuous. All right. And suppose you know y1 of X is a solution, not 0. Okay, so we're looking for that second solution. That y1's not 0. The one we're looking for, all right, is a new solution. So suppose we know that y1 is a solution, not 0. What we're looking for is a new solution, y, that's linearly independent. And what I said in the last one was that if this is the one I know, okay, so this one right here, guys, is the known solution. That's the known solution. It can't be times a constant, so I make the assumption that it must be times some function u. Same thing I did before, same steps, guys. Just a little more generic because I don't know exactly what y1 is. So I need to take the derivative on both of those. So it'll be u y1 prime plus y1 u1 prime. When I take the second derivative, I'll need to use the product rule on both of those things. So I'll have u y1 double prime plus y1 prime u prime. Product rule on that second one, y1 prime times u double prime plus u prime times y1 prime. All right, and I've got quotient product rule here, product rule there. I can, like in with the other one, I can combine a couple of them. The y1 prime, u1 prime, there are 2 of them. All right, so y1 prime, u1 prime, I added them together right here and I got that. Okay, now, same thing I was doing in the other problem, except I knew what my known solution was there. It was e to the x. I'm doing it generically now for any known solution. Okay. Like I said, it's probably easier just to watch in this case. I will now take those derivatives and that function right there, and I'm going to plug them in to my generic DE. Just like I plugged them into y double prime minus y in the last one. But now I just know y double prime plus p, y prime plus qy equals 0. P again is what you get when you do that first step of dividing through by a2 of x, and whatever's there is your coefficient function. So I plugged in y double prime, which if you look was this, so I plugged it in right there, plus p times y prime, and y prime was this thing right there, and then plus q times y, and y was u, y1. So I plugged it in just like I plugged it in before. Plugged all of those in and got that. Now, something interesting and significant happens here. And this is D, if nothing, it's just almost a nightmare of notation because you have to keep track of so many primes and subscripts and so forth. But I'm going to regroup this whole thing right here. And the way I'm going to regroup it is like this. I'm going to take all the things that have a U in them, right there, and right there. And I'm going to take them down here and pull that U out. What's left is y1 U double prime. There's the U double primes. Was only one of those. And then I'm going to pull the U prime out of this one and out of that one. That's where that came from. Now, here's the kicker here, and it's really nice, guys. We know that y1 was a known solution to the homogeneous equation. So listen up and answer the question here. If y1 is a known solution to the homogeneous equation and I plug y1 in, what will I get? If it's a known solution to the homogeneous equation and I plug it in, I should get what? Anybody? I should get 0. Yeah, I should get 0. So that thing, I regrouped that so we could see, oh, well, that's the solution I know. That whole term right there is going to drop out. That's good news because it was getting messy. Okay, what is left is this and this. And notice there that that's a second order equation. It's got a U double prime in it and a U prime. This is a known solution, so I'm not worried about that. I mean, it would be the derivative of whatever your known solution was. P, remember, is one of the coefficients when you divide it through by A2 and so on. Here's where I use reduction of order. I use it and I do a substitution to reduce its order from 2 to 1. Okay, I'm going to do that the same way I did it in the other problem. I'm going to let W be U prime, and W prime is U double prime. And I'm just going to substitute those things in it right here in this step. U double prime is W1 prime, U prime is W. So there are my variables, the thing I'm looking for. I'm really looking for W. Okay, because W is U prime, and if I can find out what W is, I can find out what U is, because I'll just go backwards and integrate. Let's look at what we got. Here is the place where in that last problem, I used an integrating factor. I don't want to use an integrating factor here. I think I can just separate this thing, and that's exactly what I'm going to do. So starting right here, and let's see, right here and here, I am going to separate this thing. So I'm going to try to solve it by separation. All right, so I'm going to leave the W prime on the left. I'm going to put this thing right here over on the right. Now remember, guys, all of this stuff is stuff you know. Y1 is the known solution, P is the coefficient solution. It's all kind of stuff you know. I'm going to write Y prime as dW dx. All right, so Y prime is dW dx. I'm then going to separate. I'm going to bring the Y over here. I'm going to divide, I mean, not Y, I'm sorry, divide by W. And then I'll put the dx over here, because all of this stuff is just a function of x. All right, so at this point, I have got it separated. All right, it's now separated. Okay, so let me scroll it up a little bit. You know what I do when I separate? I just integrate. That's what I did right here. I integrated. All right, when I integrate the left-hand side, I'll just get the natural log of W, because it was dW over W. That's the natural log of W. I actually, let me go back a little ways here. When I got to this point, I realized that Y1 would divide into that. So I just put minus P right there. So that Y1 right there. So that's how I got that minus P. And then I get this minus thing. That won't cancel, guys, because that's Y1 and that's Y1 prime. So I get this stuff right here. All right, let me go back up. And again, this is all in the book. They do eliminate a few steps, so I want to go through them with you to make sure we got everything. All right, so I'm going to integrate. I got this natural log of W. I am going to move this term right here, this one right here, over to the other side. Log W plus 2 log Y1. And I'm going to leave the minus P dx plus C over on the other side. When I integrated that, I'll just add the plus C there, okay? I'm going to combine these two using properties of logs. And when I combined them, I sort of combined two steps in one here. When I combined them, notice the log of something plus the log of something else is the product, and I brought this 2 up as a power. So what I have on the left-hand side is log of WY1 squared. What I have on the other side is just the minus integral P dx plus C. I took both sides to the E so I could undo that log. So that's what I did right here. I undid the log and I'm left with that, okay? That tells me that if I solve for W, W is this thing right here. That E to the C right there became this C1 here, guys. That E to the C became that C1. We did that all the last chapter. So notice what I've got. Notice, don't lose sight of where I'm going. What I'm trying to find is this new solution, Y, and we defined it as U times Y1. So I need to find U. I need to find U. But that's easy enough because I let U prime be W. So since I let U prime be W, I can find U. So the integral of U there will just be W. So that's what I did. I took the integral of this thing right here, and I get U as this. C1 e to the minus P dx over Y1 squared dx plus some C2. Okay? Now, here's what's you're going to see something you should remember from when I did specifically. Now what I'm looking for is the U Y1, because that was going to be my new linearly independent thing. So there was U. I took Y1 times that U, And when I added the plus C2 on here, when I multiplied by Y1 on both sides, I got a Y1 here. This is what I was doing a minute ago. Y1 was already a known part of the fundamental set. So we're going to say, I don't need that part. I just need the part that's giving me a new piece. So I don't really need that. I'll let C2 be 0. So that one drops out. It's just, I did the same thing before. And what I need to do on this C1 right here is make it as nice as possible. And as nice as possible is C1 equal 1 in this case. Now, here's the big deal. And this is where you might need to start writing down because I'm going to show you something here. The new solution that should be the new part of the fundamental set can be given to you by that. And that, my friends, is a formula we could use for any one of these things. Okay. All right, let's take a breath for a minute. I'm almost there. So all I have to do to find a new thing to make a fundamental set here is take this thing right here and just compute it over on the right-hand side. Now I'm going to show you how you can do that. You do in the first one I did. Because if I do the first one, I think you'll see where I'm plugging in things. Let me point out one other thing. This should be, if I use it with the known solution, in other words, with the Y1, if I put, and I'm proposing that that's the other member of my fundamental set, Y2, you should get a Wronskian that's non-zero. So if you did, all you've got to do now to prove that is differentiate this thing right here, and that's what'll go in the under there in your Wronskian. Find your determinant, and I'm going to tell you that when you find that determinant, you're going to get this, which is not 0, which means I have found a linearly independent solution. This will be on your next quiz right here, going from here to here, finding that derivative, finding that, the derivative of that and putting it there, and then finding your Wronskian. I'm going to put that on the next homework as a bonus problem. Okay? Finish that up. Finish that up. I'll write it out for you too, but differentiate that, put it here, find the Wronskian. I'm already telling you what you should get. You should get e to the minus integral p of x dx. And since that's non-zero, they do form a linearly independent set.
The bonus, is it for the homework due on Thursday?
Yeah. I will probably extend that homework, guys, till the end of the week since we're not even going to have class on Friday. So we'll just say, I'll just put that homework on Friday. Okay, I'll send you an email out to that effect, but I'll give you a little more time for that since we're not going to have class on Friday. But I would like it by the end of the week. So that'll be on there as a bonus. Does everybody understand what I'm telling you to do? Show that this new thing that I got, which is supposed to be my new Y2, if you differentiate that and put its derivative here. Now I'll give you a little hint here, guys. This is a function of x and this is a function of x. What do you think you're going to have to do to differentiate this? First thing I'm going to have to do is move that sign over, that determinant sign. What does that look like to you? If you're looking at this part and this part, how are you going to have to differentiate that? This is a function of x and this is a function of x. What are you going to do?
Product rule?
Yes, you're going to use a product rule. That's my hint. Okay, it's messy, but then again, it's not so messy because a lot of times, if you take the derivative of an integral, you'll just get, well, not a lot of times, if you take the derivative of the integral, you're just going to get what's in there. So just try it and see what you come up with. Okay, so here's what I'm going to do. let me leave my formula up here. There's my formula right there. I'm going to do the one I just did, but long way, that y double prime minus y equals 0. Notice, I'll just write out essentially what it looks like. Y double prime plus 0y prime minus y equals 0. Now, I write it like that because of some of the things we need in this formula. Number one, the coefficient on that is 1. I don't need to divide through by anything. But if I got something where the coefficient isn't 1 on this, I need to divide through. If I divide through by 1, which I simply get, again, y double prime plus 0y prime minus y equals 0. And that thing right there is my P. What is my Q, guys? What is my Q in this one? Not that I need it. It really didn't come up in the formula, but just so you know what it is, what's Q? What's the coefficient on the y here?
-1.
It's -1, okay? All right, so here's what the formula says. It says, take your known solution, which I knew to be e to the x. Remember, we started out saying, I know e to the x is a solution. How do I find the other one? So I put e to the x there. Up here, I put e to the minus integral of 0 because that's my p. I want you to see that's always the coefficient on the whatever there, the y prime. Okay? Over the known solution and squared in the bottom. Okay? So I've now created a formula that I can use to do this stuff. I don't have to go through that whole substitution, separate it, blah, blah, blah. I got this formula here. So e to the minus 0, guys, the integral of any constant, of 0 is any constant. So minus c, I just put c1 there. All right, e to the c1, e to some constant is c1. So that's what replaced the c1 is what replaced that, okay? Because that was a constant, and e to a constant is another constant. Down below, it said take y1, which I knew to be e to the x. Again, that y1 thing is my known solution, and I squared it. Well, y1 was e to the x. I squared it, I got e to the 2x. At this point, I pulled out the c1. I rewrote this as e to the minus 2x. And I got this. When I integrate e to the minus 2x, I get e to the minus 2x over minus 2. Okay, everybody see, I just integrated that thing. And notice that is just a constant. C1 over minus 2 is just a constant. So I'll call it C2. Doesn't really matter what C2 is because the core of this thing is that. And guess what? That is my other linearly independent solution. That's my other one. So I got this formula. And the book, interestingly, says you can do this the long way by just carrying it out for whatever your y1 is, the very first thing I did in this lecture, or you can use this formula. Your instructor will let you know. That's exactly what it says in the homework. On the homework that you have to hand in, I wrote, there are only 2 problems on there. The first one said, do it the long way. That's what I mean by do it the long way, I mean don't use the formula. I'm gonna assign that one as another bonus. This homework's gonna be mostly bonus points, guys, okay? I'm gonna assign that as a bonus. The second one says use the formula. That'll count for points. The other one will be, so when it says long way, will be a bonus, okay? So I'll write that down at the end of this so you remember that. The short way is to use the formula that we just derived because it works for everything. And there's that formula right there. Now I'm going to show you one more using the formula and we'll call it a day. Everybody okay with this? Let me scroll it up just a hair. That also said, I'll reiterate it. If e to the x was your known solution. And e to the minus x is your linearly independent other solution. And we only need 2 of them because it's second order. There's the general solution.
The C1 and C2 and the general solution is separate from the C1 and C2 that we were working with when we were solving for y.
Yeah, I was just generating those things when I integrated before. This is just your generic general solution right there, okay? All right, let's look at another one. We'll go through it and we'll just go through it a step at a time. Suppose I had this one right here. There's a second order DE. I'll try to take this a little slow, guys, so you can write it down. I'm not sure this might have been in the book, but you can write it down where. My first step always is to divide by this. If you use that as your P, you're going to get it wrong. You've got to divide by it before you identify your P. All right. So I divided everything by x squared. This came out to be y double prime. This was minus 5x over x squared. This was 9 over x squared. And of course, 0 over x squared is just 0. So first of all, divide by x squared. Divide by x squared. Okay, now, once you look at this one right here, there's your P. And if I simplify it, it's minus 5 over x. So right there, I've identified one thing I know. Here's my P. And they are telling me that this is a known solution. Now, how would I check that that was a solution, guys? Suppose I said verify y1 equal x cubed is a solution to this DE. I mean, we've been doing it all semester. How would you verify it? Anybody? How would I verify that was a solution? How do you verify anything's a solution?
Take the derivative and the second derivative and plug it in.
Take the function, the derivative, and the second derivative, plug it in there, and you should get 0. You don't know where that came from at this point. You have no idea, okay? But we know it's a solution. They're telling us it's a solution. So here's what I'm going to do. I'm going to plug everything into that formula. The formula, and I'm going to let me scroll back and look at the formula again. The formula said y1. Shoot, I'm sorry, I lost everything I had. I'm going to write it down. I'm going to write it down right in here, so I'm going to show you where I'm plugging things in. The formula is back up here. It said that the function you're looking for is y1 times the integral. The function you're looking for is, no, just y. Sorry, no, one there. Is y1 times the integral of e to the integral p dx, all right, all over x, and let me go back, all over y1 squared, okay? So in this case, I'll write down the formula, all over y1 squared, okay? Okay, so that's my formula. So I'm gonna start plugging into it. I did it. So, sorry, and I left out, there was a minus right there in the formula. We'll go back a minute. You see, there was a minus in the formula right there. All right, I accidentally left it out. Okay, so there's the formula. So my known solution was x cubed. So what I do is I put that right there. I put x cubed there, all right? Then it's e to the minus integral of p of x. Well, guys, p of x was minus 5 over x. Make sure you take the sign with it. make sure you take the sign with it. Two common errors here is forgetting to divide by the leading coefficient and forgetting to take the sign with your p, which is going to mess up everything. So I wrote that down, e to the minus integral minus 5 over x over the known solution squared. Well, that here, that was x cubed squared. Okay. Now, if I look at the numerator, this is not so bad. If I do minus a minus, that's plus. All right. And I'll do a little bit of work right down here on that, just so you see what I'm doing. It'll be e to the 5 over x. And let's see, to e to the integral 5 over x. And what is the integral of 5 over x? Well, it's e natural log of 5x, or 5. Sorry, let me get that. There's the 5 there. E5. I pulled the 5 out. Natural log of x. What I'm going to do with that is pick up the 5 as a power, and I'll have e natural log of x to the 5th. Well, e natural log of x to the 5th, the e and the log undo each other, and I will get x to the 5th. Okay? So I'm using the properties of log. So this thing right here turned out to be e natural log x to the 5th. And that's just x to the 5th. So that whole simplification of that messy thing right there was just x to the 5th. All right, so x to the 5th over x to the 6th is 1 over x. I've got everything in the formula, and I've gotten down to something I can integrate here. We know that's log x. So the basic, I could put a plus c here, but I don't need it in this case. It's going to be x cubed times log x. That's the other solution. So it was plug and chug, guys. I identified p. I was careful with my integration. I put in my known solution. That's what I get. That being said, then we've got two solutions. We've got the x cubed and we've got the x cubed log x. And if you do that bonus, you'll see that those two are linearly independent. If you do it, if you do the bonus, you'll show that's generically true, and you don't have to do it again for every single one. So, because if you put these two things right here into a Wronskian, you're going to come out with something non-zero. And that's what that bonus is about. Show it generically. Show it, I don't have to worry about it. I showed it generically. The general solution then is C1 times the one I knew plus C2 times the one I found. And that's what I have. Okay. So the only real problem in the homework, I would try a couple of these in the general homework. The only real problem you've got in the hand-in homework is to do one of these using the formula. Do one of them, try one of them the long way. And then the bonus that has to do with showing the linear independence. Okay. So actually on that homework, there'll be two bonuses. One's the Wronskian showing that's equal to e to the integral p of x dx. And the other one is the one that says on your sheet, it says long way. I give you credit if you do it the long way. The one where there's credit is just the one you have to do that says use the formula. Okay. This shouldn't take you, I mean, while it took me a long time and it was nasty notation, and not nasty, but it was just complicated notation, messy looking notation. It's easy to do it. It's pretty easy to do it once we've derived the formula, and that's what we did right here. That's our formula. You know one, you can find the other one using that formula. Okay, I'm done, guys. Does anybody have a question? Let me get the gallery out here. Let me see if I can get everybody in here. Yeah, they took it away from me again. Show grid. I put in a setting that said I could see 49 people last night. You know what? I don't see 49 people. I see various names and things, but I don't see everything. But has anybody got a question about where we are?
When did you say you're gonna make that homework due?
Let's make the homework due by Happy Friday, Good Friday. Let's just say it's Friday at 5 instead of Thursday at 5, okay? Friday at 5. That might give you a little more time. Actually, though, there's only like 1 for credit and 2 bonuses, so there's not a whole lot to do there. Send it to me whenever, but we'll put the deadline as Friday at 5 on it, okay? Anybody else? Everybody okay? All right. Some of this stuff is hard to, I mean, usually when I'm in a classroom and I have a big board, obviously I start at one end and I end at the other, and I can go back and do this and this and this. It's a little harder here, but I'm basically doing the same thing I would do on the board. Questions, anybody? All right, I'm done. Go on to your next class, whatever that might be. And I will see you on Wednesday morning, okay? All right, I will post the video as well. I've got it recorded, so I'll post it, and you can look at whatever. It'll help you if you look at it again. I posted with all the scroll on it if you haven't looked yet, so you sort of have to hear me talking and look at what I'm trying to do through all the scroll. But all right, guys, I will see you on Wednesday. Take care. Bye.
Bye. Thanks.
Bye-bye.
Bye.